Welcome everyone. Thank you for attending the August edition of our webinar. The topic for today's webinar is Maps API for automation. We will split the presentation into 4 parts. First, we'll go over the basic Maps concepts, provide an overview of the Maps GUI, discuss the new API components of Maps, and then towards the end of the session, we will provide a video demonstration of the API. So first off, Maps concepts. What is Maps? Maps stands for Message Automation and Protocol Simulation, and it is our homegrown, generic, and flexible framework for the generation of telecom protocol messages and transmission of bearer traffic, covering many TDM, IP, and wireless protocols. Maps is built on GL's proprietary scripting language, and all Maps products come with out-of-the-box scripts that act as fully functional state machines for the relevant protocol. The graphic that you see on the right shows just a portion of the protocols that we support, and a more comprehensive list is available on our website. And just to note that for this webinar, we will use SIP as the example to drive the bulk of our discussion. So Maps is comprised of 3 layers: scripts, messages, and profiles. Scripts act as the state machine for a given call and contains the logic of what message to send when. Messages are the signaling messages for a given protocol, and Maps has an inventory of generic message templates that it loads from the hard drive when transmitting an actual message. These messages are completely customizable. Because we try to keep scripts and messages as generic as possible, specific information about a call, such as the contact address for SIP, are kept inside XML profiles. Now diving deeper into each layer, scripts are written in our proprietary JS scripting language and represent generic state machines intended to provide protocol and signaling logic for establishing a call and bearer traffic. Each instance of a script corresponds to a single transaction or call. Calls can be placed in series or in parallel, which means if you place 500 calls in parallel, you will have 500 script instances all running at once. And if you place 500 calls in series, the same script will execute and terminate 500 times. It is possible to create your own scripts, and we do provide a script editor for this occasion. But it is almost never necessary, as we attempt to provide all the necessary scripts right out of the box. And moving on to messages. So when the script actually sends a message, it does so by loading a message file template from the disk. The message template can be text or binary based depending on the protocol. In this screenshot here, we're loading the invite.txt message template to send a SIP invite message. These message templates provide the actual structure of the message, and the script simply populates it with the value contained in its variables. The messages are customizable by the user. Header fields can be altered and removed. Text-based protocol messages can be edited by any text editor, but binary-based messages must be edited in our provided message editor. Because scripts are meant to be generic and reusable, specific information about a call, such as the from address and to address for SIP call, are then instead stored in profiles. Profiles are stored in XML files on the hard drive and loaded at script execution. When a script loads a profile, this is equivalent to immediately declaring and initializing the contents of that profile as variables in the script. These XML profiles are again customizable, and you can add new custom variables to any profile group. Aside from protocol generation, Maps supports traffic generation for nearly all protocols and interfaces. Traffic types include the transmission and reception of voice files in the formats of WAV, PCM, and GL's proprietary GLW format. We can send video traces in the form of GL's proprietary HDL format. We can transmit and receive DTMF and MF digits, tones, fax simulation for TDM and IP, impairment generation, and mobile data generation, such as GTP traffic. And here's a list of the industry standard codecs that are supported by MAPS. Again, more details are available on our website at the link that you see here. So all of the TDM variants of MAPS requires GL hardware to run on. We manufacture USB and PCIe based hardware solutions for T1E1, T3E3, and OC3-OC12. And all of our software and hardware platforms are Windows based. IP variants of MAPS, including the wireless protocols, can be run on any modern Windows server. A typical i7 or equivalent Xeon platform will be able to handle 2,000 concurrent calls with RTP sessions using a conventional server-grade NIC. We also offer a high-density appliance, which is for IP protocols only, that can deliver up to 20,000 concurrent calls with RTP sessions. So moving on to briefly cover the MAPS GUI. The majority of action happens in the call generation window, and as the name suggests, this is where we execute scripts to generate calls. On top of the call generation window, we provide a toolbar where you can create new script table configurations, open and save existing configurations, and choose between sequential and parallel script execution. In the middle of the window, the script table shows all the calls that are running, finished running, or are ready to be run. And at the bottom, the execution view shows the call ladder diagram in real time and provides a full decode of each message in the diagram. To build a table of scripts, you simply select the script and assign a profile. And the profile, of course, contains the information for each simulated endpoint. If you have multiple scripts in the script table, they can all be executed in parallel for load performance testing, or they can be executed in series for functional regression testing. For large volume of calls, the load generation tool provides an easy way to quickly generate thousands of calls over long durations. This tool allows you to specify the total number of calls to generate, set the max number of active calls, specify the call rate, and choose a statistical distribution. Some of the distribution patterns that we offer are shown here, and they are uniform, ramp, sawtooth, fixed, normal, step, and step sawtooth. For debugging, the GUI provides call stats and logs. Call stats provide a running tabular log of system level stats, including the total number of calls, number of active calls, number of completed calls, number of calls that have passed or failed, and instantaneous calls per second. And this is a useful tool for monitoring the overall status of large traffic loads. Similarly, message stats provide a running tabular log of all the messages that are transmitted, retransmitted, and received during the session. And this again provides an easy way to monitor the reception of error responses during load generation. There are three types of logs that the application stores. Event log contains a log of all normal script events. The event log gets populated by the event log script command, meaning this log is fully customizable. You can modify the script to report any information that the script has access to. Error log contains a log of all the script level errors. An example here would be the failure to open a RTP socket or the reception of a SIP error message. The error log gets populated by the error log script command, so this means that this is also fully customizable. The last type of log is captured error. This contains a log of all system level errors, such as the failure to open SIP sockets, script parsing errors, or unknown message reception error. But unlike the other two logs, the user has no control over what kind of errors are displayed here. And all the logs can be written to a CSV file on the disk.
Okay, and with that, I'll hand over the control to Steven, who will discuss the API portion of MAPS. Okay, thank you, Mike. The next portion of the webinar is going to cover the new features of Maps, specifically the expanded API. Currently, the Maps API only uses the Tickle language, TCL. In the latest iteration, we've expanded it out to some more popular languages, Python, Java, and VB scripts. In all cases, the language provides a simplified wrapper, so to speak, for our GLS scripts. The state machine scripts that we've written for each protocol are, in many cases, hundreds or thousands of lines and quite large, dense, and complicated, and in some cases difficult for the users to get into and really customize and modify. Therefore, we've offered these API languages as a simpler, more familiar way to control the protocols. They also, the use of an API language also offers the advantage that it permits remote control over TCP/IP connections, and additionally, it offers a many-to-many relationship between clients and servers. So a single client script written in Python, Java, or Tickle, or VB can control multiple map servers at a given time. So you can control the call initiator and the call terminator. You can control 3 servers to do conferences and redirects, things of that nature. And further, you can control servers of different protocol types, making it very easy to mix and match and create pretty complex test scenarios all within a single script. An additional advantage of the API is that the API language, be it Python or Java, can be used to control other elements of the system under test beyond just maps. It can control switches and routers. It can access databases to get configurations from the database, post results to a database. Anything you want, or anything that your chosen API language will allow, at least, can be baked into the same script you're using to control your map server, and give you further control of your system under test. Another key selling point for our existing users is that these API languages are very easy to integrate into automation test suites. We have several customers who are using Quality System Test Shell and HP UFT for their automation needs for controlling large labs with dozens, if not more, servers and devices included in the system under test. So the new languages offer a much easier platform for integration into that sort of stuff. So this will give you an idea, I hope, of what I mean when I say that the API language provides a simplified wrapper for the underlying GLS state machine. On the left-hand side of the screen, this gray box here, we can see what I would call the user-level code. This is something that we might reasonably expect you guys to be writing. So in this case, we're looking at a SIP script designed to answer a call. All the user needs to know is UAS_call dot answer _call. Answer call being the function call, UAS call being the object we're acting on. And that little bit of code there is all the user would actually need to respond to an incoming call message. This translates at the next level of code to this function, which is the API level. So when the user says answer call, what the API is doing is preparing some variables. It's issuing a user event to the map server. In this case, the user event is SIP_accept call. Then it's waiting for events. It's setting variables. So it has the baked-in knowledge of what the underlying state machine is looking for, what to expect from the state machine, and we hide that stuff from the user. And then ultimately, in the state machine itself, we're taking this user event, SIP_accept call, and this is where we're actually executing the SIP code. So this is where we handle our timers, we handle our messages, C sequences, stuff like that. The complexities of the protocol essentially are all baked into the GLS script and completely hidden from the high-level user. So this is how we're hopefully making it easy for you guys to develop your test cases and place calls and generate traffic without having to know the fine-grained complexity of the protocol or the fine-grained complexity of the GLS state machine. All of our protocols are going to come with a set of built-in signaling functions, place call, answer call, reject call, terminate call. These functions should be generic to every protocol MAPS offers, or almost every protocol. Then each protocol will have its own specific function calls too, like register and deregister. Obviously make sense in SIP, but not in other languages. So, but these are sort of this is a complexity level that you should expect to be dealing with when writing the user level code, and hopefully the complexity level is very simple. Likewise, we have built-in traffic functions. We have a different API for RTP traffic and for TDM traffic, but in each case, those APIs are generic to all the protocols. So all of the IP-based protocols will be using this same set of RTP functions, be it SIP, be it Megaco, SIGTRAN, anything else. So we let you send digits, we let you detect incoming digits, we let you switch between DTMF, MF, in-band, out-of-band. You can pick your own digit string, power, on-time and off-time if you like. Likewise, we let you send and receive pre-recorded voice files, send and receive faxes. Again, we offer pretty customizable variables. In the case of faxes, the minimum maximum data rates, what fax file to send, where to record it, how to name it, things of that nature. Send and receive tones. Again, you can use the default values, or you can completely customize the frequency and power, on time and off time for your tones. So those are the RTP actions available to you. They can be used however you want. You can do one action per call. You can do multiple actions. You could use the digit functions to completely test an IVR, traverse over the whole tree, record incoming files, stuff like that. So it can be as simple or as complex as you want it to, essentially. One of the new features that we've added to the API, in addition to just the new languages, is that we now offer complete message decode through the API. So every message we transmit or receive at the state machine level, we can now send the entire contents of that message up to the API level script. We send it, the API script will hold that message in an object, a message object, which has 4 fields: message type, message direction, message timestamp, and then the full decode. The timestamp has so far proven to be very useful for a couple of our customers. They're interested in verifying delays between, for example, call initiation, call establishment, and call termination. Now that we deliver the transmit and receive time for all of our messages to millisecond accuracy, it becomes very easy for them to calculate that stuff in the API level language, API language, and just take deltas and figure out if they're getting the delays they want and assign a quick, easy pass-fail. So that's one nice new feature. You can also use this full decode to do your own custom parsing. SIP and other languages might have a lot of custom header fields that we cannot parse using our GLS state machine. So you can just extract that text, parse it yourself in the API language using regular expressions or any other means that can be done in real time, so that you can react to those custom headers in real time as well. The second major feature we've added for our customers to the API is that we have completely integrated our voice quality analysis platforms into the Maps API. Two basic ways to do this. For RTP, we can extract packet-based statistics for all transmitted and received audio. So this is going to give you your MOS scores, your delay, your loss, your jitter, your packet counts, stuff like that. To get that information, it's just a single function call, and then it spits out all the relevant variables. You can do whatever you want with them. Again, it's another easy way to deliver a quick, easy integrated pass-fail into your test. So that's packet-based analysis. We also have integrated maps with our VQT product, which is the GUI screen you're looking at here. VQT, rather than performing a packet-based analysis, performs an actual analysis of the waveform of the actual audio. It compares a reference file, which is the waveform you're seeing at the top, to a degraded file, which is essentially just that same reference file played through a network under test or a device under test, recorded on the far side, and then compared based on the algorithm. PESC and Polka are the two main ones that we offer. In either case, the algorithm will compare the two files and spit out a MOS score, again providing a simple means of judging call quality and providing pass failure to the user. Then the third major feature we have offered in the new API is that we've broken out our functions and our scripts into high and low level functions and scripts. The high-level scripts are meant to be essentially as simple and easy as possible. The low-level scripts are meant to be as free and flexible as possible, and therefore they end up being much more complex. So what I mean by that is, in a high-level script, for example, to initiate a call, all we would have to do is issue place call. And then the underlying GLS state machine takes care of all the protocol logic for you. In the low-level script, the protocol logic moves from the GLS state machine to the API level language. So we don't have a simple place call function. Instead, we have to manually start an RTP session, manually send an invite, manually look for which messages to expect in response. The low-level scripts end up being much more complex, much longer than the high-level scripts, but they give the user essentially complete control. So that's one major feature that our users are looking for there is negative testing. They want to purposely break the protocol, see how their devices and their systems react to unexpected messages, malformed messages, just anything like that that you couldn't reasonably bake into a state machine at the GLS level just because it's too complex. You can do it here very easily. So instead of sending an invite to start a call, I could just send an arbitrary info or options or just any other message, doesn't matter, and see how the device reacts to something negative. So this is an example of a high-level script. It's a SIP script for placing a single call. And this actually represents a complete script. This is all the code you would need to place a SIP call, and it's actually even a little more verbose than necessary. If you wanted to, you could cut it down to an even smaller script. But essentially all we're doing here is initializing a few variables. And these set local variable commands are going to pass those values to the SIP script. And then once the script is armed with the appropriate information, we say myCall.placeCall. The invite goes out. We automatically process responses and look for a connection. Once we have received a connection event from the underlying state machine, we can do our RTP actions and then terminate the call. And that's basically all there is to it. This whole script could actually probably be boiled down just to the code contained in the red boxes, and you'd have a functional script. To give you an idea of a comparison, for establishing the same call using the low-level script, again, we have to initialize all of our variables. But then rather than doing the nice little place call here, we have to manually start the RTP session, manually send an invite, manually process responses, manually process the SCP and the response to negotiate the correct codec, things of that nature. So more complex, but much more flexible too. If we wanted to establish the RTP session with the wrong codec, we could do that and make sure that our device under test handles that appropriately. We could start it with the wrong P time. Anything of that nature is all doable with the low-level scripts. Yeah. This is an example of a JavaScript for the CAS, FXO, FXX API. So it's just to give you an idea of what another protocol and another language would look like. All the CAS stuff is low level, being that it's just such a simple language. But that is a complete script for CAS. This is a regression for SIP calls to give you an idea of how the API languages make complex automation relatively simple. You can, in this case, we're loading a bunch of variables from a CSV file. So rather than baking the variable declarations into the script, we can use this single script over and over and over again, making it much more portable, flexible for the users. And the script will simply take any variables defined in that CSV file and place a call for each row, and just one by one. In this case, there's only 4 lines in the CSV, but there could be 100 or 1,000. In the same Python script, we'll go through those rows one by one and place a call, analyze it for, in this case, small score, and carry on. A slightly more complex regression. Here, the Python is going to take that regression table that I boxed in red and is going to automatically iterate over every possible combination of variables. So this delivers a really easy way to generate complex test scenarios, all within a few dozen lines of code. And the main point here is just to illustrate how you can use the complex features of Python and Java and Visual Basic to do large-scale automated tests in a very simple fashion, in a very simple and very portable fashion too, making it easier for your users to work together. Now we're going to flip to a video showing this regression you see in front of you actually executed, give you an idea of what the API looks like in action.
Okay, the purpose of this video is to give the user a glimpse into what the Maps API might look like when it's actually in action. We're looking at 3 windows right now. The large dark window on the left-hand side is my Python IDE. This is where I develop my scripts. In this case, I'm going to use it as my client application to run the script and send the API commands to the server. This application is the Maps server application. When the client starts sending commands, we're going to start seeing rows of text here corresponding to each command. The server is going to parse those commands, send them to the underlying state machine, which will generate the actual SIP and RTP traffic. In the lower right, we see packet scan. This is our VoIP analysis tool. I have it configured to passively monitor my NIC for any inbound or outbound SIP and RTP traffic. Every time it sees a new SIP call, it's going to generate a new row in this currently empty table and start updating and analyzing RTP stats in real time. It'll give you delay, loss, and jitter, loss scores, packet counts, essentially every relevant packet-based variable we can offer for VoIP traffic. When I hit this play button, what's going to happen is this little line of Python magic is going to iterate over all the possible combinations of variables in this table. So the net result is that in all my calls, I'm going to call from this contact and address of record. Half of my calls are going to go to user agent 1000. Half of my calls are going to go to user agent 2000. To each user agent, I'm going to place 3 different calls, one with 10 millisecond packets, one with 20 millisecond packets, and one with 30 millisecond packets. The Python for loop here is just going to loop over all these different call types and place them automatically for me in series. So I'm going to hit the play button here. You can see these are the variables I passed for my first call. These are the commands received by the server for my first call. Here we can see the call. It's to user agent 1000. User agent 1000. We're going to get about 1,000 packets here, which corresponds to my 10 millisecond packets. That's 100 milliseconds, or 100 packets per second, and we can see that I've got a 10-second call, 11-second call in this case. Now call 2 has been placed. We're going to see half the packet count because now I'm using 20 millisecond packets. And now call 3 has been placed, and we're going to end up seeing about 333 packets here in the top row corresponding to my 30 milliseconds. If I look at the server, I can see in my first call I've set packetization time. Well, it's going to keep scrolling. So now I've come to call 4. There's packetization time 10. Now to user agent 2000. And again, we're going to see about 1,000 packets here. Now I've got my next call coming again with packetization 20 to user agent 2000. We can see that in packet scan. And we can come back over here to the pie chart and see I've got my status and my CMOS for my first call, second call, third call, etc. So keep iterating until it's done. This table can hold any different variable you want it to. It can hold codecs. It can hold any kind of SCP information. It can hold really, literally any variable that's available to MapSip can be put in this table, and this for loop will iterate over anything. This can be used to place 100 calls or 1,000 calls. It doesn't matter. So hopefully this gives you a little bit of insight into how easy it is to use these advanced wrapper languages to create complex test cases using maps. And that's all. Thank you.